All right, and okay, I'm just recording this one through Discord. But anyway, by the time I'm recording this, I do realize that I haven't done any recording in the complex number, and I'll get that finished hopefully soon in kind of like close time for now. All right, so welcome. For now, we start with a Fourier series. So Fourier series are kind of like a strange theory, a series that probably you guys haven't ever seen before. I have seen it before. But anyway, so before we start anything with a Fourier series, I want to start a simple harmonic oscillation. Why? Because I just want to go through the revision, or I would just say simple harmonic motion, just to be more precise. I just want to be reviewing to the sine and cosine functions, so that we kind of have a sense of what's going on in here. And also one of the reasons why it is crucial to start with sine and cosine thingy, because Fourier said that everything just oscillate, right? So we said that everything oscillates. So let me just write this one down. Everything oscillates, and that is the main reason why when we talk about the Fourier Fourier motion or Fourier series, I'm sorry, Fourier motion, Fourier series, including sine and cosine function. Okay, so let's start with a simple harmonic oscillation. So a simple harmonic motion is something that easy to be depicting. Is the easiest one would be the pendulum one. So where you have a something that's swinging back and forth. Okay, so usually when we picture the simple harmonic motion, so we so the simple harmonic motion is depicted by. Okay, so we have the following graph that it just go into the top, into the peak of the amplitude, and it's just going a circle round. Because again, imagine like a pendulum thingy, it just swing it back and forth, just the same as like going into a circle, just like that. Okay, so this this radius though is the amplitude of A. So the same here, this is the amplitude A of the wave. So this is gonna be your amplitude. Okay. This is gonna be A as well, right? And also you have kind of the angle right here. Okay. And uh, the velocity that kind of going through here, you can say the angular velocity or something like that. So we can have the following of the angle, by the way, theta, if anyone remembers, is omega times t, meaning angular velocity times the times t. And of course, if you have the angular theta, you can calculate the y coordinate, the x coordinate at any point in this graph right here. For example, I want to find the y coordinate. So y coordinate, I can use the following for yt is equal to a times y is sine of theta, which just also mean that sine of omega times t at the angular velocity times t. The same thing that same thing with the x coordinates. So just a review. So you have x coordinate, that means x of t is equal to a times cosine theta is equal to a times cosine omega t. Okay, that's the general idea of what's going on here. So let me just scroll down so I can write something else. Okay, so what would be your omega in here? So that's my interest in here. What would be my really omega is actually is angular frequency. So my bad in if I did brought that one out, saying that it says omega is angular velocity, but it can be angular. I don't know. But anyway, omega here can be also be in a function of 2 pi over t. And this time is omega is actually the angular frequency. Anyway, so what we're doing over here is actually finding the position yt and xt in the simple harmonic motion at any point given. So when, for example, I have, well, yt, so let's say y of t is the position. So you can also do this with xt too. Is the displacement. Sorry, let me just write about. Okay, so let's say yt is the displacement. So if I want to find the velocity, so all I can do is I take the derivative, that equals vt. Well, just put a little y there, just making sure that we're on the right track. So we just use it. I'll just do the derivative of the first order derivative for this one here. So you have cosine here. Okay, and so the similar thing if you want to find the acceleration, you do the second derivative in terms of a position, or the first derivative in terms of not in terms of, but the first derivative of the velocity vyt, then you get the acceleration. So in the end, I'll let you work that out. So the acceleration is someone spam just called me again. But the acceleration here now is actually negative. So let me just, ayt is actually negative a times omega times sine of omega t. Okay, so that is the overall that is the overall in a nutshell for the simple harmonic motion. I don't know why it just it's jumping back and jumping up and down. It's shaking like that whenever I move the thingy. Weird. But anyway, I don't know why. Weird. Okay. So when we talk about this, is what just a simple wave, a simple like pendulum swinging back and forth. Now, what about traveling wave? Because traveling wave is a little bit different. Because traveling wave, we need to know the position, and we kind of like, yeah, that's the main point we want to know. Unlike here, we only need the time is kind of enough, right? We can see that it's omega t, things like that. But what about traveling wave? Well, we need to know the position dependence too, and that's equivalent. So when we have to write down the position, a times sine of kx minus wt. And this is a general form of what's going on here. Oh, by the way, this is going to be a replaced by a y0. I think it should be general in the same sense of the a just now, the y0. So in this case here, you have k is the wave number, and in this one here, k is equal to 2 pi over lambda. Okay, and same thing with omega. Omega is, like I said, is angular frequency. Okay, frequency. So that's why it's equal to omega is equal to 2 pi over t. Okay, so that's something we've been discussing about. And of course, that if we want to find, let's say if I want to find the frequency, the normal frequency, then it's gonna be omega over 2 pi. It's just flipping around thingy there. But this is something to keep in mind. All right. So we kind of we kind of knowing this. So what about velocity from here? I mean, in terms of velocity, I mean, I'm talking about the speed, and I didn't mean the velocity because we don't get the direction in here. But in terms of speed, we have v is equal to f time lambda. Well, this one is omega over 2 pi, and you have time 2 pi over t, and so this all cross out, you have omega over t. So that's how you find the velocity, the speed, I mean. Okay, so now if, for example, note if I going back to here, if I set x is equals 0 or t is equals 0, then it become a one variable thingy. So again, I'm just saying. I think you you already know about that. I'm just saying. So if I'm not neither, but either x equals 0 or t is equals 0, we get uh, the expression of y of a simple harmonic motion in respect to x or t respectively. Oops, t or x respectively. Okay, just something that you already know, so I'm just writing down just for fun. Anyway, now we are relating everything I'm saying here to a complex number. Now I did notice that at this time here when I'm recording this video, I didn't do anything about the complex number, but I'll get that done soon. But if I had to relating this relation to the complex number, okay, so if I have the time to uploading that, for sure I'll do it. Okay, so remember, remember here I expressing this one in terms of sign, right? So what I do is I can think that what if this is kind of like a form, what is this is a form where cosine of the remaining thing is straight to 0 and things like that. But just ignore about the cosine. I don't care about the cosine. I only care about the sine here. So, or all the other way you can think, all the other way you can think is that when you look into this one here, my bad, I should have said, what if you have, well, let's say you have kind of like a real number, like this I call it y1 plus I is y0 of kx. So this is y1. I don't really care what this y1 is, by the way, minus omega t, right? So I don't care what this y1 really is. It can be cosine, something in there. I don't care. But all I say, oh, this one can be written as the imaginary part of the complex number of yxt. This is something that I'm more interested in. So this is where I can get to this form right here. Something to note it. So that means if I have to write a symbol, I'm so sorry about the laggy causing on the screen when I'm scrolling back and down, up and down. It just all of a sudden it's just jumping up and down, right? I don't know why it doesn't appear like that in my tablet. But if I have to relate again, if I have to relating back to that sign to the complex number, I can actually write something like y is equal to y is not times e to the power of kx minus omega t. That is something that I can write, and just I have to say I have to take my note to myself and just take either the real part of y or the imaginary part of y. And that's it. Because then I can get back to the sine and the cosine function. It just take either one of them. Okay. Now let's do a sample. Let's do a sample exercise to see what's going on here. So sample exercise. Even I don't even know how to spell exercise. Exercise. Hopefully this is the right way to spell exercise. Find one, the magnitude, two, the frequency, three, the velocity, well, can be the maximum velocity, maximum velocity of a simple harmonic. So allow me to say simple harmonic motion as SHM. Allow me to do that, please. All right, so I give you everything in terms of a complex form first. So we'll deal with the complex form because in the sine and cosine form, it's kind of easy-ish to kind of deal with that. So 2t plus 3 pi. All right. Okay. So if you need a couple minutes to work these things out for sure, feel free to do so. If you feel like you don't need it, you can just continue the video. So pause the video if you need the time to solve it. Feel free to pause it, and if you don't like you don't know how to do it, or you just don't want to do it, feel free just to continue this video here. All right, find the magnitude. Well, straight away I know the magnitude of this, right, is 4. So I don't really need to do anything about that. So magnitude is 4. So anything before the sine and cosine function, they are magnitude, 100%. And now the second thing is we have to find the frequency. Okay. Now if I scroll back up here, remember that imagine if you pick x or t is equal to 0, you having back to yourself the one symbol harmonic motion. Sorry, one symbol harmonic motion with only one variable. Well, kind of something ish to down here. Okay, so I know the difficulty here when we face this problem here is 3 pi right there. So, but again, we only care what we care about. We care about the 10 to 2t here. So whatever the t here, we only deal with this one. So we don't really overthink about this 3 pi. I've seen lots of people, it's kind of like confusing with this 3 pi a lot, but if the question not asking for it yet, so don't stress that out. Okay, so this is gonna be your omega for sure. So since the omega is equal to 2, okay, so that means, so remember the omega is what, 2 pi over t, right? And so that means ut is equal to 2 pi over 2, and that's equal to pi. So that's equal to frequency is equal to 1 over pi, right? So you can actually relating back to the equation that I just wrote right here. You can actually using that equation to solve the question right away. Feel free to do anything you want. I'm just step by step here. All right. So the third one is the maximum velocity. I don't know why maximum velocity on written note. I would love to use the word velocity than the maximum velocity. I don't know. But anyway, to find the velocity, well, we know that this is giving me a position, right? So to find a velocity, all I have to do is do a derivative, right? And of course, like what variable should I derive it with? So what variable do I have? I only have t variable here. So I'll derive this one in t variable because I don't see any x in here. So ignore the x. All right. So I'm gonna say dz over the x. Sorry, dz over the t. And like as I said, ignore the s, and I just put x in there. All right. So we have, well, what do we have here? So we have minus 4 e to the 2t plus 3 pi. Just kind of write everything down here because e to the power of x derivative is equal to itself, and it's equal to bring everything down. I think this is not the maximum. I think the question asking for the amplitude. of the velocity. Oh, I feel amplitude of the velocity is the same at maximum velocity. Okay, that makes sense. Okay, my bad. I didn't realize that, but okay, that makes sense. So I have this equal to, well, this is chain law. Wait, why did I say equal? Chain law, and then I have this one. Then I have negative AEI 2t plus 3 pi here. So that here is your amplitude. So that means your maximum velocity, or should I say the amplitude of the velocity is equal to 8. This is the desired result. All right. So just a nutshell again. So simple harmonic motion. You can write thing in here in term. You can think about the pendulum when we talk about the simple harmonic motion, and you can easily draw a circle right there. The amplitude is always the radius of the circle, and the angle is treating like a displacement that's equal to angular velocity times t, right? And you can write the position in using the trigonometry relation, and this is angular frequency. I have no idea why this is not called the angular velocity, but I hope, I don't know. I don't know. But anyway, W here, for some reason here, is a angular frequency. And of course, if our angular frequency is 2 pi over t, all right, so if anyone who know why omega here is defined at 2 pi over t, in this one here, it's probably, I think probably this one is should be angular velocity. Not like the whole equation, but I should be writing the angular velocity here. But whatever, okay. And then you have, well, let's say you have this displacement. You can first do the first derivative to get the velocity. If you want to find the second derivative, you get the acceleration. Now for traveling wave, you always have two variables because you need the position dependence and also the time as well. So if you want to turn it back to one variable, you either put the position is equal to 0 or the time is equal to 0 to itself. Then you got it. So usually for a simple harmonic thingy, you have a question is kind of something like this. But anyway, I mean for this chapter right here, I will ask for magnitude, frequency, and all those things, velocity and things like that. Hopefully, I will make one video solving the problems, and we can go along with that. For now, I'm think I will record the next one, which is the Fourier series. So we start the Fourier series on the next video. Okay. And hopefully, I'll do a video of solving all the problems as much as I can for the simple harmonic motion. Cool.